now describe climate natural forcing, including galactic variations, orbital variations in Milankovitch theory, sunspots, plate tectonics, volcanism and natural greenhouse effects, as well as natural albedo. What causes climate change? Humans started emitting greenhouse gases only after the advent of the industrial era, which began in the late 1700s. Given that there were fairly large temperature fluctuations well before the 1700s, what are the reasons for these climate changes? The sun is Earth's main energy source. The sun's output is nearly constant, but small changes over an extended period of time can lead to climate changes. In addition, small changes in the Earth's orbit affect how the sun's energy is distributed across the planet, giving rise to ice ages and other long-term climate fluctuations over many thousands of years. Our objectives here are to describe how the sun's output affects climate change, as well as other natural processes that may influence climate change. The Earth's temperature is influenced by many factors. These factors are known as climate forcings. Prediction of the future of Earth's climate requires a thorough understanding of these factors. There are two categories of forcing factors: external, or outside of Earth and its atmosphere, for example, solar energy, and internal, or factors originated on Earth, for example, greenhouse gases in Earth's atmosphere. Some of the internal forcing factors are due to human actions, and others occur naturally. All external forcings occur naturally. These include galactic variations, orbital variations, and sunspots. We will first focus on naturally occurring forcing factors, that is, external forcings and natural internal forcings. Let's talk about external forcing factors and galactic variations. Our sun lies in the Milky Way, a swirling spiral galaxy of more than 200 billion stars. Every 150 million years or so, our solar system rotates around the Milky Way. The quality and quantity of energy reaching Earth from nearby star systems and from the gases and dust that pervade interstellar space vary during this rotation. The cyclical fluctuations in this energy are so long and so uncertain that they obscure the influence of galactic rotation on Earth's climate. Nonetheless, several major climatic events, such as tropical temperature changes, are separated by about 150 million years, and therefore may be related to the period of galactic rotation. Let me repeat this due to its importance. Several major climatic events, such as tropical temperature changes, are separated by about 150 million years, and therefore may be related to the period of galactic rotation. Since 1979, when we began taking measurements from space, the data has shown no long-term change in total solar energy, even though Earth has been warming. Let's repeat this as well. Since 1979, When we began taking measurements from space, the data has shown no long-term change in total solar energy, even though Earth has been warming. Now, let's talk about orbital variations in Milankovitch theory. Relying on ice cores and sediment cores from the deep ocean, scientists have learned that the ice age cycles of the past 3 million years are caused by periodic oscillations of the Earth's orbit. These oscillations do not greatly affect the amount of sunlight that reaches the Earth, but they do change the distribution of sunlight with latitude. The distribution matters because land and water absorb and reflect sunlight differently. And the distribution of land and water is quite different in the northern and southern hemispheres. Again, ice ages occur when, as a result of orbital variations, the Arctic regions intercept relatively little summer sunlight, and ice and snow do not melt as much. Orbital variations are characterized by their eccentricity, obliquity, and precession. Let me elaborate. But once again, before we elaborate, orbital variations are characterized by their eccentricity, obliquity, and precession. Now, let's elaborate. If the Earth were a disk with its surface perpendicular to the rays of sunlight, each point on it would receive the same amount of radiation, an energy flux equal to the solar constant. However, the Earth is a sphere, and aside from the part closest to the sun, where the rays of sunlight are perpendicular to the ground, its surface tilts with respect to the incoming rays of energy, with the regions furthest away aligned in parallel to the radiation, and thus receiving no energy at all. The elliptical shape of Earth's orbit around the Sun is characterized as its eccentricity, a measure of the deviation of an orbit from a perfect circle. The red line is a near-circular orbit, and the blue line is an elliptical orbit. Eccentricity varies like a combination of two periodic functions. The smallest period has a period of 100,000 years, as you can see here. Earth's daily rotation around its own axis has an angle with respect to its orbital plane around the Sun. This angle is called the axial tilt, or obliquity, as you can see here. If the axis of Earth was perpendicular to the plane of its orbit and the direction of incoming rays of sunlight, then the radiative energy flux would drop as the cosine of latitude as we move from equator to pole. However, as we can see in this slide, the Earth axis tilts at an angle of 23.5 degrees with respect to its plane of orbit, pointing towards a fixed point in space as it travels around the Sun. Once a year, on the summer solstice, or about the 21st of June, the North Pole points directly towards the Sun, and the South Pole is entirely hidden from the incoming radiation. Half a year from that day, on the winter solstice, or on about the 21st of December, the North Pole points away from the Sun and does not receive any sunlight while the South Pole receives 24 hours of continued sunlight. In these photos, you'll see maximum tilt angle, present-day tilt angle, and minimum tilt angle. Notice the periodicity of the variations of the obliquity. Obliquity has a 41,000-year period. Earth behaves like a wobbling top, and its precession, the alignment of its axis of diurnal with its distance from the Sun, oscillates with an average period of about 21,000 years. Due to this wobble, a climatically significant alteration must take place. The tilt toward Vega means that the northern hemisphere will experience winter when the Earth is farthest from the Sun, and will experience summer when the Earth is closest to the Sun. This coincidence will result in greater seasonal contrasts, as you can see here. Here is the orbital variations in temperature variations with time. Taken together, the variations in these three cycles create alterations in the seasonality of solar radiation reaching the Earth's surface. These times of increased or decreased solar radiation directly influence the Earth's climate system, thus impacting the advance and retreat of the Earth's glaciers. The episodic nature of the Earth's glacial and interglacial periods within an ice age is caused primarily by cyclical changes in the Earth's circumnavigation of the Sun. Variations in the Earth's eccentricity, axial tilt, and precession comprise the three dominant cycles, collectively known as the Milankovitch cycles. They are named for Milutin Milankovitch, the Serbian astronomer who was generally credited with calculating their magnitude. Taken together, the variations in these three cycles create alterations in the seasonality of solar radiation reaching the Earth's surface. These times of increased or decreased solar radiation directly influence the Earth's climate system, thus impacting the advance and retreat of the Earth's glaciers. Let's repeat this once again. Taken together, the variations in these three cycles create alterations in the seasonality of solar radiation reaching the Earth's surface. These times of increased or decreased solar radiation directly influence the Earth's climate system, thus impacting the advance and retreat of the Earth's glaciers. Currently, the obliquity of Earth's orbit is intermediate. Its eccentricity is small, and its precessional alignment is such that Earth is farthest from the Sun during June and July. If the orbital variations were the sole forcing factors, Earth's climate would remain about the same for the next 40,000 years or so. Let's repeat this. If the orbital variations were the sole forcing factors, Earth's climate would remain about the same for the next 40,000 years or so. Now, let's talk about sunspots. Here are examples of sunspots. Each of these sunspots have an area spanning several times that of Earth. Periodic changes in the alignment between the Sun's rotational axis and the gravitational center of the solar system produce intense fluctuations in the vertical magnetic fields of the Sun. These divert heat flow from deeper layers in the Sun and generate patches of fluctuating temperatures on the surface that manifest as sunspots. Optical telescopes can be used to detect sunspots. The number of sunspots varies. There is an approximately 11-year period, as well as a less predictable, longer cycle. Solar energy reaching Earth increases during the time of high sunspot activity, therefore increasing the Earth's surface temperature. However, the sunspots account for only a 0.03 degrees Celsius variation in global temperature. Now let's talk about plate tectonics. Orogeny is the process by which tectonic movements of Earth's crust or volcanic activities form mountains. Mountains disrupt global atmospheric circulation. Mountains tend to accumulate ice and snow that increase the percentage of solar energy reflected by the Earth. The uplifting of mountains also exposes rocks that undergo chemical weathering and absorb carbon dioxide. In the distant past, drifting continents make a big difference in climate over millions of years by changing ice caps at the poles and by altering ocean currents, which transport heat and cold throughout the ocean depths. Times of relatively rapid mountain building, say from 40 million years ago, when the Himalayas and the Sierra Nevada first arose, until today, as these ranges continue to uplift, are usually cooler periods. In this photo, mountain ranges intercept wind and water vapor, causing rain shadows, concentrated rainfall, and other climatic effects. Tectonic uplift also exposes land to chemical weathering, which removes carbon dioxide from the atmosphere. Epeirogeny is the formation of continents and ocean basins through deformations of Earth's tectonic plates. The global distribution of landmass determines the amplitude of glacial-interglacial cycles. Mid-ocean ridges release large amounts of energy and greenhouse gases. The sea level rises and falls as new plate materials modify the shape of ocean basins. Let's talk about volcanism and natural greenhouse effects. Volcanic activity releases carbon dioxide and water vapor, which cause atmosphere warming. Volcanic ash and sulfur dioxide gas from volcanoes reflect solar radiation, causing regional or global cooling. The June 1991 eruption of Mount Pinatubo had a global impact. The sulfur dioxide, or SO2, in this cloud, which was about 22 million tons, combined with water to form droplets of sulfuric acid, blocking some of the sunlight from reaching the Earth, and thereby cooling temperatures in some regions by as much as 0.5 degrees Celsius. An eruption the size of Mount Pinatubo could affect the weather for several years. Let's repeat this. The June 1991 eruption of Mount Pinatubo had a global effect and a global impact. The sulfur dioxide, or SO2, in this cloud, which was about 22 million tons, combined with water to form droplets of sulfuric acid, blocking some of the sunlight from reaching the Earth, and thereby cooling temperatures in some regions by as much as 0.5 degrees Celsius. An eruption the size of Mount Pinatubo could affect the weather for several years. In April of 1815, the cataclysmic eruption of Tambora volcano in Indonesia was the most powerful eruption in recorded history. Tambora's volcanic cloud lowered global temperatures by as much as 3 degrees Celsius. Let's repeat this. In April of 1815, the cataclysmic eruption of Tambora volcano in Indonesia was the most powerful eruption in recorded history. Tambora's volcanic cloud lowered global temperatures by as much as 3 degrees Celsius. Even a year after the eruption, most of the northern hemisphere experienced sharply cooler temperatures during the summer months. In parts of Europe and North America, 1816 was known as the year without a summer. A significant amount of greenhouse gases in the atmosphere is due to past natural forcings and is not the result of human actions. Let's talk about natural albedo. The amount of water vapor in the air varies considerably, from practically none at all to as much as 4% by volume. Water vapor is the source of clouds and precipitation. It has the ability to absorb heat energy given off by the Earth, as well as some solar energy. Water vapor is therefore important when we examine the warming of the atmosphere. Clouds reflect sunlight back to space and also act like a greenhouse gas by absorbing heat leaving the Earth's surface. Low clouds tend to cool or reflect more energy than they trap, while high clouds tend to warm or trap more energy than they reflect. The net effect of cloudiness on surface temperatures depends on how and where the cloud cover changes. This is one of the largest uncertainties in projections of future climate change. One major pattern of ocean currents, the thermal haline circulation, or global consurface belt, involves the northward flow of warm surface waters from the Caribbean along the Atlantic coast of the United States. It is known as the Gulf Stream. Let's repeat this. One major pattern of ocean currents, the thermal haline circulation, or global consurface belt, involves the northward flow of warm surface waters from the Caribbean along the Atlantic coast of the United States. It is known as the Gulf Stream. The deep oceanic circulations are driven by fluxes of heat and fresh water that change temperature and salinity of the water. Dense water, which is cold and saline, sinks deep down, creating a worldwide circulation as light water, which is fresh and warm, which upwells through the world ocean, affecting the global sea surface temperatures, which in turn changes the dominant mode of climate variability. Ocean waters circulate around the globe in established patterns or currents that derive from different factors, including differences in solar energy received by the equator and the poles, topography of the seafloor and coastal land masses, changes in seawater density, rotation of Earth around its axis, and atmospheric winds. In summary, the timing of the ice ages are essentially the result of the Earth's orbit. But the orbital variations do not explain neither the slow pace of the Earth's descent into the cold phases of the cycle, nor the abrupt recovery to interglacial warmth. Large climate swings, from glacial to interglacial and back, are caused by relatively small changes in the distribution of sunlight with latitude. Finally, let's talk about human forcing, including greenhouse effects such as hydrogen, carbon dioxide, methane, and nitrogen. Again, many chemical compounds found in the Earth's atmosphere act as greenhouse gases. These gases allow sunlight to enter the atmosphere freely. When sunlight strikes the Earth's surface, some of it is reflected back toward space as infrared radiation, or heat. Greenhouse gases absorb this infrared radiation and trap the heat in the atmosphere by re-emitting infrared radiation. Most of this section is a summary of our earlier description of the greenhouse effect. Over time, the amount of energy sent from the sun to the Earth's surface should be about the same as the amount of energy radiated back into space, leaving the temperature of the Earth's surface roughly constant. In other words, over time, there is a natural balance between positive, or warming factors, and negative, or cooling factor forcings. Human actions are introducing forcings into the climate system, which are altering this balance and thus causing a change in the Earth's temperature. We characterize these forcings as human. Let's repeat this. It's very important. Over time, the amount of energy sent from the sun to the Earth's surface should be about the same as the amount of energy radiated back into space, leaving the temperature of the Earth's surface roughly constant. In other words, over time, there is a natural balance between positive, or warming factors, and negative, or cooling factor forcings. Human actions are introducing forcings into the climate system, which are altering this balance and thus causing a change in the Earth's temperature. We characterize these as human forcings. A rising concentration of greenhouse gases from deforestation, agricultural practices, and fossil fuel burning produce greenhouse effects through the emissions of H2O, CO2, CH4, CFC, and more. Rising concentration of particulate matter from agricultural burning, cultivation, and fossil fuel burning are aerosols. Alteration of Earth's surface reflectivity by deforestation and desertification are albedo. Increase in high cloudiness caused by aircraft contrails are clouds. Because human actions affecting climate change originate on Earth, we can consider human forcing as internal. Our objective now is to describe human forcing factors, or anthropogenic factors. Let's look at greenhouse effect and carbon dioxide. We have very good correlation between carbon dioxide concentration and temperature. "400,000 years of greenhouse gas in temperature history is based on bubbles trapped in Antarctic ice. The time scale has been expanded for the last 150 years, which is on the right side of the diagram. Carbon dioxide and methane levels are far above the range of natural variation in the current geologic era. The last time carbon dioxide was greater than 300 parts per million was about 25 million years ago. Nitrous oxide, or N2O concentrations, have primarily risen because of agricultural activities and land use changes. Ozone, or O3, forms naturally in the upper atmosphere, where it creates a protective shield that intercepts damaging ultraviolet radiation from the sun. However, ozone produced near the Earth's surface via reactions involving carbon monoxide, hydrocarbons, nitrogen oxide, and other pollutants is harmful to both animals and plants and has a warming effect. The concentration of ozone in the lower atmosphere is increasing as a result of human activities. Black carbon particles, or soot, which is produced when fossil fuels or vegetation is burned, generally have a warming effect because they absorb incoming solar radiation. Black carbon particles settling on snow or ice are a particularly potent warmer. Halocarbons, including chlorofluorocarbons, or CFCs, are chemicals that have been used for a variety of applications, such as refrigerants. In addition to being potent greenhouse gases, CFCs also damage the ozone layer. The production of most CFCs are now banned, so their concentrations are starting to decline. Deforestation and other changes in land use modify the amount of sunlight reflected back to space from the Earth's surface. Changes in land use can lead to positive and negative climate forcings locally, but the net global effect is a slight cooling. Most aerosols, or airborne particles in droplets, such as sulfate, or SO4, cool the planet by reflecting sunlight back to space. Some aerosols also cool the Earth indirectly by increasing the amount of sunlight reflected by clouds. Human activities, such as industrial processes, produce many kinds of aerosols. The total cooling that these aerosols produce is one of the greatest remaining uncertainties in understanding present and future climate change. Let's repeat this. The total cooling that these aerosols produce is one of the greatest remaining uncertainties in understanding present and future climate change. Here is an illustration of contrails over Paris rooftops. Jet airplanes flying at high altitudes generate contrails. These behave like clouds in that they reflect incoming solar radiation and decrease daytime temperature maximums, but absorb long-wave radiations from Earth's surface and increase nighttime temperature minimums. Contrails have the potential to diminish temperature differentials between day and night. Commercial air traffic was shut down in the United States for 3 days on September 11th through the 13th in 2001, following the terrorist attack. During this interval, day-night temperature differentials in the United States jumped by 1.8 degrees Celsius. This information was provided by Travis and colleagues in 2002. The change was significantly greater in the regions where contrails are most abundant. Here is a comparison of the anthropogenic and natural forcing of the climate for year 2000 relative to the year 1750. The height of a bar indicates